Fossil fuels kill about 8 million people every single year, which is more than the populations of Aotearoa and most of the remaining Pacific Islands put together. And they will continue to claim many, many more, of course, as the planet continues to boil due to climate change, which is due to fossil fuels. Nuclear power, though, the one that evokes all of that terror and fear and, well, fair enough, because radiation sickness is terrifying. But that has so far, in its entire 70-plus year history, killed fewer than 200 people. Granted, that's a bit more complicated, but we'll get into that later. But if you bring this up on social media, man, do people get mad. So kia ora, welcome back. I'm Brianne West, and I am fascinated by nuclear energy ever since I found out that Chernobyl happened on my birthday, albeit the year before I was born. But still, fascinating. Now, some of you are probably a little bit surprised by that previous 8 million people killed every year by fossil fuels number, because the one that you think will be the highest, nuclear, isn't. In fact, it's one of the lowest. It's one of the safest ways to create energy that we have. So it begs the question, if nuclear's fatality rate is orders of magnitude lower than coal's, why are we still burning coal like it's 1890? But I also wanted to address this because a lot of people are really surprised to hear that I am pro-nuclear energy, because obviously I'm an environmentalist and therefore you can't be both. They're mutually exclusive terms, also Greenpeace would have you believe. And actually, it nearly lost me a job with Greenpeace. Years ago, I think I was 18, just started at university, and they were advertising for those people on the street. Yeah, I was one of those annoying people who accost you as you walk into malls. I do apologise. I walked into the interview, which was half a day long, by the way, and involved role-playing, which was hell on earth. But I walked in, and one of the first questions was, what do you know about Greenpeace? And I don't remember what I said, but I did talk about how I was super pro-nuclear energy. The interviewer interjected and said, do you know what Greenpeace was founded on? Because, of course, one of Greenpeace's founding principles and its origin story, if you like, is nuclear power and how it would kill us all. A great lesson in doing prep for your job interviews. But first, let's start with radiation 101. Right. Everything around us is atoms. You may have heard the saying, all that exists is atoms and empty space, and actually empty space is the vast majority of it. Every single one of those atoms around us was forged in space. Like I said, you are quite literally made of stars, and if that doesn't interest you in particles, I don't know what will. The lightest, which is hydrogen, and most of the universe is helium, they were minted in the first 3 minutes of the Big Bang. Anything heavier was created later inside stars, so carbon in the cores of red giants, for example, oxygen in massive stars on the brink of collapse. But the real heavyweights, the ones that have got the most protons and neutrons in the nucleus, which we're going to talk about in a minute, like gold and iodine or uranium, they need much bigger forces, such as what you find inside supernova or neutron star collisions. Those cosmic events quite literally spray those elements around the galaxy, where they're clumped into new solar systems and eventually make their way into everything, including your cells. So yeah, that neighbour you think might be a bit weird, kind of technically an alien almost. But what is an atom? If we're going to carry on using the idea of space, an atom is like a mini solar system. So you've got the compact nucleus, which is the sun, for example, and that's made of protons and neutrons. Protons are positively charged particles and neutrons are neutral, so they have no charge. And that nucleus is orbited by electrons, which are the negatively charged particle/wave that you've probably heard of because of electricity. I said before, all that exists is atoms and empty space. Well, atoms are actually mostly empty space because the nucleus is minuscule beyond belief. It's about 1/10,000th the width of the entire atom itself. The electrons, like an electron cloud, are orbiting around the outside, and that big gap is just empty space. In a normal atom, the positive charge of the protons in the nucleus are counteracted by the negative charge of the electrons floating around it. It's electrically neutral. If you remove or add an electron, that atom then becomes reactive, and that is the basis of chemical reactivity, because the atom wants to be neutral. So it will snatch or drop an electron from a neighbouring atom to get back to that neutral level. But that literally changes the element, because that's how the element is identified, if you like, as the number of protons. If you add a proton to a nitrogen atom, which has 7 protons, you get an oxygen atom. If you take away a proton from a sodium atom, you make neon. But chemistry can't really do that in nature. That's the kind of thing that nuclear reactions do. So that's radioactive decay, particle accelerated collisions, like in the Large Hadron Collider that you may have heard of, or smash-ups inside stars. That needs a lot of force. Now, if you keep the proton number, but you change the number of neutrons, you get an isotope. So it's the same element, new mass, no change in charge. And this is where you will see numbers after elements. You may have seen something like carbon-14, for example. Well, most carbon is carbon-12. So that means it has 12 protons, 12 neutrons, 12 electrons. That is a balanced atom. But some carbon that exists in nature is carbon-14. So that means it has 2 extra neutrons. So carbon-14 has 2 extra neutrons, and that leaves the nucleus lopsided. So after about 5,730 years, that's called a half-life, the amount of time that half of a sample has decayed, and one of those neutrons will change into a proton. I am not going to go into that process. That's complicated and we don't need it this episode. But again, we're talking about balance. So the atom will fire out a high-speed electron to keep the balance. That is something called a beta particle that we are going to come to soon. So the charge is now balanced again. The nucleus has gained one positively charged proton, so it has changed into a different atom. And the electron that's shot away in a tiny flash of gamma light, that is the energy that makes the clicks you hear on a Geiger counter, because that is radioactivity. So that was a little bit technical, and I hope you have stayed with me, because a wee bit more technicalness coming up. It's worth it. Hang in. Ultimately, radiation is if the neutron to proton ratio in an atom isn't balanced, it calms itself by emitting energy or a particle in some way, shape, or form. Now, broadly speaking, there are 2 types of radiation, ionizing and non-ionizing. As I mentioned, an ion is an atom that has a different number of electrons to protons, so it's either positively or negatively charged. Radiation that is energetic enough, so it has enough oomph to knock electrons off other neighboring atoms, is called ionizing radiation, because it can create ions from ordinary atoms. Now, that is important, because ionizing radiation can knock electrons out of DNA molecules, and that is what ultimately can lead to cancer. And of course, all of the other horrific symptoms of radiation sickness. But there's also loads of different types of lower energy radiation. Visible light would be a great example, but there's also radio waves, there's microwaves. They can heat up or jiggle molecules if you like, but they cannot break chemical bonds because they simply don't have the energy. Therefore, it's non-ionizing, and you don't have to worry about your cell phone anymore. So there are 4 main types of ionizing radiation. The biggest is an alpha particle. It's 2 protons and 2 neutrons, which is actually the nucleus of a helium atom, so it doesn't have the electrons. It's very ionizing and has a lot of energy, but it's also very slow. So they are easily stopped by the outer layer of dead skin or a piece of paper or clothing. So they can't penetrate from the outside. However, they are extremely dangerous if you ingest an alpha particle emitter through inhalation or swallowing. Then you have beta particles. These are those high-speed electrons that are ejected when a neutron changes to a proton. They penetrate through a few millimeters of tissue, but thin metal or plastic will block them. Then you have the biggies that you may have heard about, which is gamma rays and X-rays. They are high-energy light. X-rays are produced outside the nucleus. Gamma rays come from the inside. Same physics, different origin. They have no mass, but they are very deeply penetrating because they are high energy, and they do the most damage. Those are the things that you need dense shielding from, like lead and concrete. Finally, you have neutrons, and they are the most important for today's conversation. Being neutrons, they are neutrally charged. But when they fly out of a reactor core, they are moving at thousands of kilometers a second, which is somewhat hard to imagine. And the danger is in the insane kinetic energy that brings with it. They are easily absorbed or moderated by hydrogen-rich waters like water or deuterium, which is just an isotope of hydrogen, or, interestingly enough, plastic. But you don't really have to worry, because unless you're hanging out near or inside a nuclear reactor, or you take a lot of very high altitude flights, so much higher than your commercial flight, you're probably never going to come across them. Each isotope has its own way of getting rid of its energy based on its atomic structure, and that is why we see these different types of radiation. If you've got very heavy atoms, such as radium-226, they're too fat to split neatly. So they shave off compact alpha particles, which are the 2 neutrons and the 2 protons, and there's a dash of gamma rays on the side. Then you look at uranium-235, which is, of course, what we typically use in nuclear power plants. That decays very slowly on its own until a slow neutron gives it a nudge, and then it flies apart in what we call fission. That releases epic amounts of energy, more neutrons, and plenty of gamma rays. And that is exactly what you want in a controlled chain reaction like you find in an operating nuclear reactor, or a well-operating nuclear reactor.